Welcome back. Now we would like to transition to another one of our projects within the Transformational Aeronautics Concept Programs, TTT, or the Transformational Tools and Technology Project. TTT, or T cubed, develops state-of-the-art computational and experimental tools and technologies that are vital to NASA Aeronautics' ability to advance the prediction of future aircraft performance in flight. I would now like to welcome to the stage Mujeeb Malik. Mujeeb is involved in the TTT effort, Aircraft Certification by Analysis. Mujeeb, welcome to Imagine Aviation.
Thank you, Steve.
I'll turn it over to you for your presentation, and then I'll come back on for some questions and answers. Take it away.
Thank you, Steve, and good day, everyone. Let's talk about aircraft certification by analysis. At the outset, let me say that I'm talking about a limited portion of the certification, that is the CFR, that's Code of Federal Regulations, Title 14, Part 25, Subpart B, that deals with aircraft flight, and also Part 33, Subpart F, that deals with engines. If you attended the opening session of Imagine Aviation, you heard Pat Melroy, NASA's Deputy Administrator, where she talked about the tremendous impact NASA's wind tunnel had on the progress of aviation. During 1940s and 50s, there were huge investments in building wind tunnels, which allowed testing of a large number of aircraft that were designed, tested, and built during that era. Those wind tunnels, well, those that have survived, continue to play a very important role in aerospace vehicle design. During late 1960s, a new tool for aircraft design emerged called computational fluid dynamics, or CFD. The present-day computers are over 1 billion times faster than they were then, 55 decades ago. And during this time period, we have made tremendous progress in developing numerical algorithms to efficiently harness power of these computers. As a result, the use of CFD tools is prevalent for aerospace vehicle design, many other industrial applications, as well as in several NASA missions. One can get an idea about the impact of CFD on aircraft development with that the number of aircraft wings that were tested prior to 1980 was about 50 to 70 to reach an optimal design, which reduced to about 10 by the time Boeing 787 was developed in 2005, all due to CFD. And the design of aircraft wings now primarily depends upon a CFD. So therefore, it's time to ask the question, can aircraft certification be done by analysis method in lieu of flight testing or for the engine's ground testing? So before we answer this question, let's watch this brief video, which is an old one, but will give you an idea about certification flight testing.
From dragging the airplane's tail on the runway to flying head-on into fierce crosswinds, Boeing pilots have been pushing the 787 Dreamliner and moving ever closer to certifying the all-new airplane.
When we do these big tests, it's a big deal because it is the test.
After spending weeks on the road, flight testing in multiple locations, 787 Chief Test Pilot Mike Carricker returned to the office for a brief break and described some of the tests he and the team have been conducting, such as takeoff performance.
You start with regular takeoff, like we recommend the airlines crews to do all the time. And then what we do is we go around and we look at how much you can vary from it. You rotate before the predicted airspeed, you rotate after the airspeed, you rotate too fast, you rotate too slow, and it's all to define that there's a tolerance for error.
There was little margin for error when Captain Carricker maneuvered ZA001, the first Dreamliner, for a takeoff test called Velocity Minimum Unstick, or VMU. This test establishes the lowest speed the airplane can leave the ground and requires putting the tail on the runway carefully.
You don't want to hold the tail in the ground because that's actually a big brake and it'll slow the airplane down. You will never get up to its takeoff speed. But then again, you can't let the tail come up because then you're missing your data. And so the idea is to get the tail down quickly, smoothly, and just hold it on the ground. Just hold it on the ground, and then hold that attitude, and then you have to fly away.
Next up, landing the Dreamliner on very wet pavement. Crews dumped more than 50,000 gallons of water on an ungrooved runway. Then Captain Carricker had to pull off 2 landings.
We do one with the manual brakes, and then we do another one using the airplane's automatic braking system. We demonstrate that the tires spin up and that the anti-skid system works per design. And we use a normal technique for the pilots, so they don't have to do anything different.
Wet is one thing, windy is another. ZA002, the second Dreamliner, fought winds of 30 knots to prove the airplane is designed to handle high crosswinds.
One of the kind of conditions that requires more piloting skills.
Dan Mooney, Vice President of 787-8 Development, explains how the pilots position the plane for landing.
The pilots actually crab the airplane to angle the nose of the airplane into the wind. At a certain point, the pilots will begin to turn the airplane back down to line up with the runway just in time for touchdown.
We're really doing well in the airplane part, and it's very exciting to see all these individual parts starting to be added up.
And soon, Captain Carricker and the team will be back up in the air to test some more.
So these and many other tests are required by regulatory agencies like in US FAA before they will certify the airplane to be put in service. So currently, as I mentioned, flight testing is the main means of compliance with these regulations. For engines, it's ground testing. So but we would like to explore the alternative means of compliance based on computational tools for aircraft certification in the 2 areas I mentioned. There are many benefits of doing that. First, there is potential for huge cost savings. There are estimates that certification flight testing costs something of the order of $1 billion for a major aircraft development program. And about 2/3, well, at least a large fraction of the testing is done in the area of high lift. That is where an aircraft is in takeoff or landing position. If we can supplant 50%, for example, of the testing by computations, then there is potential for savings of hundreds of millions of dollars in an aircraft development program. CBA also makes the certification process more efficient and streamlined. No scheduling challenges that may be encountered in flight testing due to weather and other factors. Some anomalies sometimes appear, for example, unexpected vibrations that could be found during flight testing. In that case, the manufacturer has to go back and investigate the cause and then provide a fix for that, and again go back for testing. This is a very costly and time-consuming proposition. So with computational tools, the process can be accelerated, reducing time to market. And the question is, why don't we use analysis method for certification in lieu of flight testing currently? This figure in the bottom here shows the flight envelope, load factor versus speed. And in the middle, there's a hashed area in this oval marked by yellow broken line. That's the area where current CFD tools work well. And this is the area where aircraft is flying in the cruise condition. So the tools are currently used in the design for that portion of the flight envelope. But as we go towards the edges of the flight envelope, for example, these areas which have stalls in it, the flow separates, and the current tools that are the RANS-based, Reynolds Average Navier-Stokes CFD, they don't work well there. And so we need something better than that. Even though we have, as I mentioned, computers are a billion times faster than they were 50 years ago, we still cannot compute those governing equations from first principles, so modeling is involved. Currently, these equations are solved where all the turbulent motions are modeled. And it's estimated that it may take 80 years or even more to solve these equations from first principles. But for engineering application, we really don't need to solve those equations from first principles. So there are intermediate solutions available. Can you go to the next slide, please? So we commissioned a study to develop requirements for aircraft certification by analysis. The objective of this study was to develop the requirements for certification by analysis and to establish what will it take to use CBA as an alternative means of compliance with the certification regulation, what are the current gaps, and then develop a research roadmap to develop the technology to reach the objective of CBA. So this work was done under a contract with Boeing, and their team members included Pratt & Whitney, an engine manufacturer, and two universities, Stanford University and University of Wyoming. The report came out last June, and it's available at NASA technical report server. Anyone can download from there. The research roadmap that was developed is a 20-year vision for aircraft or engine certification using computations. So since a significant fraction of the flight testing is in the high lift region of the flight envelope, that is where aircraft is taking off and landing, so it makes sense to focus on that application first. And this is also a region, as I mentioned, most of the testing is done. So as is suggested in the report, this will require computational tools that employ scale resolving methods for prediction of aircraft maximum lift. The region where current RANS-based tools do not provide reliable results. A particular scale resolving method is called wall model large eddy simulation, or WMLES. The thin flow region near the aircraft surfaces where flow velocity reduces from the free stream value to 0 at the surface is called boundary layer. So in WMLES, about 10% of this boundary layer near the surface is modeled, as in RANS, but in the outer 90% of the boundary layer, turbulent motions or eddies are computed or resolved. So this is a compromise between accuracy and computational cost. So we in the TQ project, as a result of a previous VN study called CFD Vision 2030, have been investing in this area of tool development in past few years. And it appears now that this technology can be used for the intended purpose of computing high lift flows. How do we determine that a tool has reached that we can now use it for that application? How do we validate a computational tool? So for that, we conduct wind tunnel experiments and obtain experimental data. So this figure here in the middle here is one such attempt where this model was tested in a kinetic tunnel in the United Kingdom. This work was in collaboration with Boeing. And in this wind tunnel test, we obtained experimental data at different angles of attack of the wing and obtained this curve of lift versus angle of attack and at a certain flow conditions. And then This model is called highly common research model because this is a non-proprietary model. So we have three currently under TQ sponsorship, three efforts ongoing on developing valve model LES capability. So valve model LES has been implemented in two of NASA CFD codes, LAVA at Ames Research Center and Fun3D at Langley's Research Center. The third effort is under a grant to Stanford University, which has carried out pioneering research in this area. So this figure here compares the results of experiment with one of the CFD code LAVA. And so the red symbols here are computed using LAVA code, and the black symbols are experimental results. So you can see there is good agreement in this maximum lift region. And the report, the CBA vision report specified that for engineering application, they need computational tools which can predict this maximum lift within 2% of the experimental measurements. And all three codes that I mentioned, LAVA, Fun3D, and the Stanford code, Charles, can achieve that now. So valve model LES is, since we are now resolving part of the flow field, not modeling, is more expensive than the traditional RANS-based CFD. So first, next step is to improve the computational efficiency by better exploiting the high-performance computing hardware. We also need to establish best practices in terms of problem setup, numerical grid generation, automating the process for this technology to be used in industrial settings. We also need to acquire experimental data at additional flow conditions, and there are plans to do that in next 2 years in NASA Langley's National Transonic Facility. That data will then be used for additional validation of the computational codes to increase the confidence level for their industrial use. I should point out that the high fidelity computational tools that we are developing can be used not only for CBA application, but for several other NASA missions. For example, during past 2 days, you have heard about future X-planes and flight demonstrators, which go beyond the traditional tube and wing configurations. So these high fidelity computational tools, which are more physics-based, can be used for performance prediction instead of wind tunnel testing for those applications as well. Similarly, these tools can be used for analysis and design of flight on other planets. For example, how would a future human-rated capsule land on Mars safely, knowing that it will be an order of magnitude heavier than a robotic mission? So these tools are used there. The T-Cube project's role in CBA is to develop the computational technology, and while doing that, collaborate with academia and industry, and then transition the technology to other NASA missions and industry. I should mention that for acceptance of CBA as an alternative means of compliance for certification, industry deals with FAA directly and tries to convince them that this technology has reached at a stage that they can be used for the certification process. But NASA still can work and will work with FAA in an advisory role during that process. Finally, I should point out that I have only talked about a small sort of limited area of technology focus that is used in CBA, but overall CBA is much broader, requires much broader suite of heat transfer. All those areas are discussed in the report that the CBA Vision 2040 report that I mentioned, which provides a 20-year vision for this technology development. And so with that, I would say that I would end. Steve?
Yeah, thanks, Mujeeb. That was excellent and interesting presentation and conversation. Video was a nice context to it. I'll welcome people to throw in questions into the IL tool. We have a few, so I'm going to jump in with them. This might be a tough one to ask, but we might as well throw it out there because I know it's in a lot of people's mind. But what is the time frame in which CBA will really become a reality?
So that's why the vision was 40-year vision, right? 20-year visions, 2040. But we are taking it, we have a shorter term vision also. So that's why we are trying to attack the high lift part of it. And those tools, I think we are close to getting it validated. And the objective is that next 5 years or so, we should be ready to employ these tools for those applications.
No, nice. So that helps us get a little bit of flavor of the state of the art of your current computational tools, especially in fluid dynamics. But what advances do you think are needed to really enable or for everyone to embrace CBA?
Well, I mean, for limited to this particular application, of course, we need to have the tools. We need to develop uncertainty quantification so that the user can know what the limits of this answer that we'll get from using the tools is and whether that's acceptable or not. So eventually, once we are satisfied with these tools, the manufacturer, in this case, for example, Boeing, will have to see whether these tools, whatever flight data they have available, how good they are compared to that data. And so they need to satisfy themselves before they use these tools and go to FAA. Now, in other areas, of course, they're like for Buffett and these tools are continuously being developed, but expanding the footprint of this CBA with using computational tools. And similarly, these tools have their use in engine applications also. So there's another need to be more emphasized for engine certification. So this research roadmap that is developed in this study provides a systematic approach for all those things, easier part, at least what is we can accomplish next 5-year, 10-year, 15-year time frame. So it goes in progress in a systematic manner.
So you're hoping that roadmap you're alluding to, that will help NASA play a role in enabling that certification by analysis. Is that true?
That will help NASA and industry. I mean,
okay.
NASA only develops, as I mentioned, technology and encourages its use. Industry is the one who has to sort of get satisfied with it, go to FAA, and see how they respond to that.
So what type of validation experience? Oh, I'm sorry. Go ahead.
So it's a process, right? It's not just to go ahead.
Right. So the validation experiments, what type are needed that would help, that maybe NASA can play a role in to help industry with that adoption?
So as far as the wind tunnel experiments are concerned, they're already we are in the plan in next 3 years. There is a number of experiments that will be done in NASA Langley's wind tunnel. And this is an area where, of course, other countries are interested. Airbus is interested, right? So there is a plan that Airbus and even in Japan, the same model or similar models will be taken to their wind tunnels, and they will provide data also. Now, one can go beyond wind tunnels and have some flying test bed also. This is a possibility on the horizon, but I mean, there's no current funding for doing that. But I think
right.
the next step to do that.
Okay. I also assume supercomputers are going to play a role in enabling CBA. Can you talk to us a little bit about that?
Oh, yes, that's a critical area because the high fidelity tools that we use for this analysis require supercomputing. And especially these wall model LES technology, since we are resolving a big part of that boundary layer that I mentioned, that's more expensive. So, and when you are designing something, you need to do a lot of computations. And so computing is critical for this application. And not only for the application that I mentioned, but as we go to for engine certification and other maneuvers, it becomes more and more challenging and more supercomputing is required.
So we've talked a lot over the past couple days about NASA's role in technology development and assisting the private sector in the marketplace. This fits right into that. Do you have any idea what the economic benefit and how this could be and how this would enable the enhancement or advancement of civil aviation by using CBA?
Yeah, so CBA, of course, has economic advantage. It reduces the time to market for manufacturers, and it helps provide more efficient designs. So sustainability, we've been talking about that. More efficient design means less carbon footprint. And even the certification process becomes more streamlined. And so the cost of aircraft development is greatly reduced because of that. Even within NASA also, any future concept explains and demonstrators, those can be more efficiently analyzed and designed and developed. So.
Excellent. Time for one more quick question for you, Mujeeb, from the IO tool. What do you think has been the biggest advance in CFD over the past 10 years, and how has it enabled in aircraft design?
I think the biggest is the progress in the hardware. We have now, traditionally we have been using CPU-based hardware, and now we have GPUs and graphical processing units, right? And now some of the cores like Fun3D have been ported to GPUs, and they perform 4 or 5 times better if you compare based on the same energy usage or the cost of the hardware basis. So that is one advantage. And
nice. Go ahead.
These applications, since we need a lot of computation and more expensive computations, then that hardware is really beneficial.
Oh, that's wonderful. Well, we're out of time. We could go on for a while talking about this. This is very interesting. This is actually very revolutionary. And so we want to thank you very much for sharing this with us, Mujeeb. Great presentation, great Q&A session regarding your work on aircraft certification by analysis. Thank you very much for joining us today.
Thank you, Steve.